We'll talk about an example of value factorization in electrical engineering. So let's say we have this circuit which is V1, which is the input terminal, I1, so this is an input terminal, and this is your output terminal. Let's say this is I2, this is your V2, this is output terminal. So so the relationship which transform this VI1 to V1 to I1 to V2 to I2 is called transfer characteristics. It's called transfer characteristic. It is more similar to the transformation that we discussed in our early lectures, that what AX does is transform this X by using A, and it converts this X to another column matrix which is B. So in this case we can say that V2 I2 is A times V1 and I1. So this circuit has some transfer characteristics given by A which convert this input voltage V1 I1 to V2 I2. Okay, now let's assume if we have a circuit like this, right, which is I1 here, V1 here, and of course this point is I2 and this point is V2, right? So it is more like a series circuit. We can say right here is V2 is equals to V1 minus I1 R1 and I2 is equals to I1, right? So I can write this in the matrix form, which is equals to V2 I2 is equals to 1 minus R1, 0 and 1, and that is V1 and I. Similarly, if I have a parallel circuit, let's say, which is, let's call this as V2 and this as R2, this is your I3, this is your I2, right, and this is your V3. Okay, so in this case we can easily see that your V2 is equals to V3 is equals to nothing but equals to V2. Okay, and I3 is equals to minus V2 divided by R2 plus I3, right? This is quite obvious from the direction of the currents, that this current I3, if we say, is the superposition of the current in this branch and this branch, right? The current will be flowing over here, but the thing is we have the minus here to indicate the current is going in the opposite direction. So these two currents will add up, right, and will generate I3. Okay, so in this case the results will become simply as V3 I3, it becomes equals to 1 minus 1 over R2, 0 and 1. Okay, now now what we can do here is we can cascade this these circuits, which can be like that, right? Which is here R1, I1, and which is here is I2. The voltage here is V2. This is V1, and again this is R2. This is your I3. Again, this point is I2. This point is V3. So we can simply write here V3, the transfer characteristics, which is from V3 I3, right? And if you want to write from the perspective of V1 I1, you can write that how you transferred characteristics from V1 I1 to V2 I2, and then transfer characteristics from V2 I2 to V3 I3. So as we have previously calculated, right, this one is the transfer characteristics A of from V1 to V2, and this is the transfer characteristics from V2 to V3 and I2 to I3. So the result can actually be written as V3 I3 can be written as in the product of these two, which is nothing but equals to 1 0 minus 1 over R2 minus 1 and 1 minus R1, 0 and 1, and this is equals to V1 into I1. Okay, now it means this can be written as V3 I3, and you can simply multiply. So you can think of this one as an upper triangular matrix and a lower triangular matrix, because this is you can see here, this is a lower triangular matrix and this is actually your upper triangular matrix. Okay, this is, we know, coming from a series circuit, this is coming from a shunt circuit. Okay, now this is here can be written as 1 over minus 1 over R2 and minus R1, 1 plus R1 over R2. Okay, okay, right. So we generally can see here the series circuit here is producing a lower triangular form, and the shunt circuit is producing an upper triangular form. Now if let's say, for example, we want to have a desired characteristic from V3 to V1, from say V1 to V3, to have 1 minus 8 minus 0.5 and R. We can compare the corresponding values to the members in this matrix and calculate the values, right? So for example, in this case we can directly get R1 is equals to 8 ohms, right, and 1 over R2 is equals to 0.5 ohms, right, and which gives us R2 as 2 ohms, right? So we can simply calculate those values to get the desired transfer characteristics from V1 to V3. Okay. Now the next topic that we are going to study is a very important topic, and this is which is called the subspaces. Okay, so generally we have defined up till now the space Rn, right, but today in this lecture we are going to define the subspaces of R of n, and of course it depends on the vectors that it contains. So before we go further, let's define it first, and then we'll see how subspaces are formed and how we calculate the basis for that subspace. Okay, so we say a subspace of Rn in any set H in Rn has three properties. The first one is the zero vector is in H. Okay, so all zero vector is in H, so it means this should be in H depending on n. Okay, now second one is any vector that is for each u and v, which are different vectors of course, in H, right, the sum of u plus v, the sum u plus v is in H. Okay, and the third property is for each matrix, for each vector u in H, right, and scalar say c, the vector c times u is also in H. Okay, now so what these three properties tells you is, the first one is the zero vector is in H, okay, depending on which subspace that it exists in, and for any matrix u and v, the sum u plus v is in H, and if you multiply any vector that is in H by a scalar compound c, then that cu vector is also in H. So in effect, subspace is closed under addition and multiplication. Okay, right? Now say, so if we say if there is v1 and v2 vectors are in Rn, right, are in Rn, in the space Rn, right, so the H is span of v1 and v2, right? So span, we know that is nothing but is a linear combination of all the vectors v1 and v2, right? And because this is the span, generally we write here is as so we know it's a linear combination of v1 and v2. So let's look at the first property, which is the zero vector should be in H. So it means linear combination of v1 and v2 is the span, so 0 times v1 plus 0 times v2, and this should be is a linear combination, and it is stating that H contains 0, so H has 0. Okay, so the first property of this is satisfied, right? Now let's say two arbitrary vectors, which is u, let's say, which is say s1 plus v1 plus s2 v2, and let's say v is equals to t1 v1 plus t2 v2, and I add them up, right? So that vector should also be in the subspace, right, the second property. So it means s1 plus v1 plus s2 plus s2 into v2 plus t1 times v1 plus t2 times v2. I can write this as s1 plus t1 into v1 plus s2 plus t2 into v2. So we know that these are scalar quantities. Okay, so it means so it's a linear, nothing but the linear combinations of v1 and v2, so it means this is also satisfied. Okay, now also for any scalar quantity c here, right, so cu you can actually see is also in H, because this becomes nothing but equals to c times s1 v1 plus s2 v2 is equals to cs1 plus cs2 into v2. Of course, C is a scalar, s1 is a scalar, c is a scalar, s2 is a scalar, so it means the multiplication is nothing representing a linear combination of v1 and v2, right? Okay. Now the other important property here is, let's say if v1 is not 0, let's say if v1 is not 0 and v2 is some multiple of v2, let's say b times v1, then actually then v1 and v2, right, simply span a line through the origin. Okay, so line through the origin is another example of subspace, right? I mean, the question you should probably be asking, why we need to look at the subspaces, right? One of the very good application of subspace is linear block codes, right? And we often use that to transmit signals. In generally, if you want to have error detection capability in your transmitted signal, what we do is basically make use of the subspaces to transmit the signal. And of course, what it does is basically it allows the receiver the flexibility to not look for the whole set of changes in the space. It has to look for the changes that are possible in a subspace. Okay, but we'll talk about that hopefully when you get to your 6th or 7th semester. But you have to remember this very basic, that subspace have two important properties. First one, it contains zeros. Second one is for any vectors u and v, which is in the subspace, the sum u plus v is in H, and for any u and in H and scalar c, the vector cu is also in H. In effect, we are saying that subspace is actually closed under addition and multiplication. Okay, and actually another property that we have just discussed is that the span of the vectors actually also forms a subspace, because from just the calculation we carried out in this example. Now, so the thing here is, we can now generalize this thing here, that v1 to vp in Rn, right, the set of all linear combinations of v1 to vp is a subspace of R of n, is a subspace of R of n. We can now start saying that the span of, which is actually v1 to vp, as the subspace spanned by or in fact generated by v1 to vp. Okay, now another, since we are dealing with the matrices, right, not only vectors, we are dealing with the matrices, we can also define on similar lines the column space and null space of a matrix. Okay, now the column space of the matrix A, say the column space of a matrix A okay, is the set CL, denoted by COL, capital C, not a small c, COLA of all linear combinations of the columns of A. Okay. Now, the question you might be thinking, why we need to define the column space of a matrix? Because we will see in a very short while that solution of this kind, Ax is equals to B, is only possible if B is spanned by A, the column space of A, right? If it is not spanned by the column space of A, X will not have any solution, right? We'll just see in next few examples. Okay, so if A is equals to A1 to AN, so with the columns in Rm, indicating that A is an M cross N matrix, right? So each column has M. So each column vector has M entries. Okay, now the column space of so if A is equals to A1 to N with the columns in Rm, the column A, now this is the set, remember this is the set of the linear combinations of A1 up to Nn is the same as the span, right? And all the linear combinations of vectors are represented by the span of those vectors. So this is that. So column space for matrix, the set column A of all linear combination of the columns of A. So if A1 is the column, A2 is the column, up to An is the column, with the columns in Rm, because an M cross N matrix, so it means the entries that we'll have here is, let's say C1 up to Cm, for example. Okay, so M entries, so it's in space Rm. Okay, the column A is the same as span A1 to An, because the linear combination of the vectors is represented by the span. Okay, okay, let's do an example. The example that I was talking about, at how the column space, this column COL set can be used to find the solution of the system of linear equation. So let's say this is a matrix A, which is 1 minus 4 minus 3 minus 3 6 and 7 minus 4 minus 2 and 6, and B is equals to 3 3 and minus 4. Okay, what we have to do is actually determine whether B is in the column space of A. It is equivalent to finding the solution Ax is equals to B. It means all the possible set of scaling coefficients that these vectors must have to make it equals to B, right? And we know that that is the set column of A. It must be contained in column of A if such a linear combination exists, right? And so it is equivalent to finding the solution set of solution set of system of linear equation, and by using an augmented matrix. So simply we can see here 1 minus 4 minus 3 minus 3 6 and 7 minus 4 minus 2 and 6, and you get here 3 3 minus 4, right? So I can do the sequence of operations here, that I can multiply the first row with 4 and add it into second row, and of course I can multiply the first row with 3 and add it in the third row, and similarly I can reduce it further. Okay, so if I do that, like, so let's do that to reduce to this set here, which leads me to 1 0 0, and you multiply with this with 4 added here, so that becomes minus 3 minus 4, it will remain the same. This will become 6, this will become minus 2, this will become 3 again here, sorry, this will become 4 times, so minus 16 plus, So that will be minus 18, and this will be 4 times 8, 12, and 12 plus 3, that will be 15, and that will be minus 2, that will be minus 6, and that will be 5 here. And again, what I can do here is divide this by 3 and add it here, okay, and which will leads me, if I do that, right, that will leads me to the following here, which is 1 minus 3 minus 4, 3, 0 minus 6 minus 18 and 15 and 0 and 0 and 0 and 0, right? Now, no, you know that this is an augmented matrix, right? Remember this. Now, we can see here, what we can see here is the solution is actually consistent, because this is 0 equals to 0, so there is no anomaly here. So what we can see here is because it is consistent, right? So it means that this matrix P here is actually being spanned by the columns by the column A, or it means what we're saying here, it is because column A is a set containing all the linear combinations of these columns 1, 2, and 3. It means it is in that present in that set, which is COLA. And so we can say here, since AX is equals to B is consistent, okay, probably doesn't have a unique solution, but and B then B is in column of A, right? Okay, now as we have defined the column space, now we can actually define the null space of the matrix. And null space of a matrix is the set name A. Okay, so null space, we can define null space. So here, so null space of a matrix A is the set null A of all solutions of the homogeneous equation AX equals to 0, right? So all the possible set of solutions, right, of the homogeneous equation for which AX is equals to 0 is the null space of this matrix A. Okay, so it means so when A has, let's say A has n columns, the solution AX is equals to 0 belongs to Rn. Okay, and null space of set A is subset of, and the null space of A is a subset of Rn. Okay, in fact, I mean, if you look at this definition, right, so in fact you can say the null A, which is the set of the matrices, set of the vectors, actually you can say the set null A is has the properties of a subspace, has the properties of a subspace Rn. Okay, now now this is very important because generally we have dealt with this form earlier as well, right? and we know that solution for this kind of equations can be written in a parametric form if it has got free variables. Now or it can also be used to check the independence of the vectors, or independence and dependence of the vectors. And now to test whether a given vector a v, to test if the vector v is in null A, okay, what we have to do is just compute AV should be equal to, see whether AV is a zero vector, right? So we have to see if A is being multiplied by B, it should yield 0, right? So the simplest test here is for any vector that you see that if it is in null A, you say, okay, if AV is equal to 0, it means it is in null A. If it is not, then it means it is not in the null space of A. Like the one in the previous case when we try to solve the equation, if this vector B is in the column space of A, right? We found out that it does, because when we try to solve it using a augmented matrix, the solution was consistent. It means there exists the possible linear combinations of the column vectors which will yield the vector B. Okay, now so the next topic that we after defining this, the next important topic that we are going to study today is called the basis for a subspace. Okay, now this is also very important, because what happens is that a subspace can actually contain an infinite number of vectors. I mean, because if you can see, if there are vector v1 and v2, because span of v1 and v2 define a subspace, right? Now in that case there are infinite linear combinations of v1 and v2, so it means there are infinite many vectors that is present in the subspace, right? So the problem is how we can actually represent a subspace by a minimum number of vectors, because we cannot actually say which vectors to use to represent the subspace. So we have to identify the set of vectors that can completely, they are minimum in nature, right? There should be minimum vectors, there should be minimum number, and they should completely define the subspace. Okay, so remember this. So we define the basis for a subspace a basis for a subspace H. Remember this, that we have already defined the subspace H of Rn is a linearly dependent set in H that spans H. Okay, so as I've already defined, that H is the subspace, and it must follow the three properties that we discussed: that it contains a zero vector, and second one, it is closed under addition, and the third is it is closed under multiplication. Now, and we remember this. Say for example, very simple example of a basis of Rn can be these three vectors, right? So E1 is equals to, let's say, 1 0 0 0, and so on and so forth, and E2 can be 0 1. Okay, and similarly you have En can be 0 1 here, right? So these are the columns of an invertible n-by-n matrix form a basis for all R of n. Okay, because they are linearly independent and spans R of n. One such matrix, I mean, example I have shown you already, is an identity matrix, because if it is an identity matrix, so that can actually be dealt with in a form that can form the basis of a subspace. Okay, So we can say that in this scenario the set E1 up to En is called the standard basis. It's called the standard basis for Rn. But for any subspace H, right, Rn is a linearly dependent set in H that spans H. I mean, the condition here is, it means that it should able to cover all the sets in H by the simple linear combination of this linearly independent set in H. Okay. Now this basis can be for any subspace, right? We have already defined two kinds of subspaces, which is the column space, denoted by COLA, and the null space, which is defined by null of A, right? So let's do an example and try to find the basis for one of, let's say for the null space, right? And let's say we've been given the question, find the basis for the null space of the matrix, the following matrix, right, which is A is equals to -3, 1, 2, 6, -2, -4, -1, 2, 5, 1, 3, 8, -7, -1, and -4, right? Okay, remember this, as I told you earlier, right? So if I say any null space is nothing but equals to all the possible set of solutions of x for which Ax is equals to 0, right? So this matrix becomes in a parametric form, can be written as 1, if I do the row operations and all that, right, becomes simply add 1 -2 0 -1 3 0 0 0 1 2 -2 0 0 0 0 0 0 and 0, right? How did I obtain this matrix? Actually what I did was I had this matrix A, right, and I augmented it with the 0 matrix here because it is for the basis for the null space. I mean, you don't have to do it, but the thing is, because we are defining the null space, it is important to write it here for your understanding, right? So once I did that, right, then what I did was I actually carried out the row operations and try to convert it in a form which gives me a solution for x, right? But when I did that kind of operations, the row operations, I found out that this last row actually comes out to 0, and of course I left with only these two rows, right? And I cannot do any further operations. Actually what I can write here is as this thing as x1 minus 2x2. It means indicating here that I might have free variables to play with, and this is minus x4 plus 3x5 equals to 0, and then we have got x3 plus 2x4 minus 2x5 equals to 0, and the last row is 0 equals to 0. Okay, so as you remember from the last lectures that we did before this lockdown period, so we can find the basis sets or the linear independent sets as simple manipulations here, which is 2x4 minus 3x5, and again x2 will remain x2, x3 will become minus 2x4 plus 2x5, and this will remain x4, this will remain x5, and I can write this in the form which is x2 as 2 1 0 0 0, and then I can write this as x4 which is 1 0 minus 2 1 0, and again x5 as minus 3 0 2, 0 and 1 here, right? So what we can see here, so the all possible set of the null space of A, okay, and that means, so if you look at here, right, this equation here, so I can write this in a very generic form here, using that as the vector x2u plus x4 v plus x5w, right? So this is your left hand side is actually x, right? x1 to x5, right? So we can see here that the null space of this this matrix A that we have just written in the previous exam, just in the previous page, was spanned by actually three vectors, because u, v and w, and all possible set of linear combinations of u, v and w, because x2 and x4 and x5 are the free variables which we are free to use. So all possible set of linear combinations of u, v and w actually will give will span the whole the whole null space of this matrix A. So so we can write this as the vector u, v and w, right, generates null of A. Okay, and the thing here is u, v and w actually are linearly independent, because remember this is x1, x2, x3, x4 and x5 on your left hand side, right? So only thing, remember this, in the case of linear independent, there is the factor linear combinations of those vectors, right, will only have trivial solution. Any linear combination that will have a non-linear trivial solution, right, will not have the linearly independent vectors. Here we can see here, because we are solving for ax is equals to 0, only time that becomes 0 is when x2, x4 and x5 are zeros, right? So in this case u, v and w are actually linearly independent. It's also a linearly independent set. So as we have defined, what is the basis? Basis here is a basis for a subspace H of Rn is a linearly independent set in H that spans H. So we can see here that u, v and w are a linearly independent set as defined for to find the basis, right? So which is here, right? And also it spans the whole null space of the vector A, okay, because any possible set of linear combinations from x2, x4, because we are free to choose x2, x4 and x5, so any values of x2, x4 and x5, the linear combinations through which we can actually span the whole null space of A, okay? Okay. Now as a next example, as we have find the basis for the null space of A, right, let's try to find the basis for any of a vector of a matrix for its column space, okay? So let's say find a basis for the column space of the matrix, which is B equals to, let's say, 1 0 0 0 0 1 0 0 minus 3 minus 3 2 0 0 5 minus 1 0 0 and 0 0 1 0. Okay, now so we can easily see here, so these are the columns here, right? So these are the columns here. So it's got 5 columns, right? So we can write this B1, B2, B3, B4 and B5. We can easily see here, I can actually quite easily see here, the B3 can be written as minus 3 times B1 plus 2 times B2, right? And now similarly b4 can be written as something like 5 times b1, because all the rest entries are 0, and minus b2, right? So the fact that b3 and b4 are the linear combination of the pivot columns means that any combinations of b1 to b5 is actually just a combination of actually b1, b2 and b5, right? So so we can say the column space is nothing but the span of b1, b2 and b5, right? Remember, this column space, how we define the column space, right? It's nothing but the span of the vectors in the matrix, right, of the column matrices, right? Because b3 and b4 can already be written in terms of b1 and b2. The span here is or the matrix or the space here is actually being spanned by only these b1, b2 and b5, because b3, b4 can be simply generated by b1 and b2, and any combination of b1 and b2 might cover this b3 and b4. So it means these are not these vectors are in the span of the column space, but sorry, these vectors are there in the span, but not necessarily contributing towards finding the basis for that column space. Okay, so in this case, if I write this as if v is any vector in column B, right, so I can write this as c1 times b1 plus c2 times b2 plus c3 times b3 plus c4 times b4 plus c5 times b5, since c1 b1 plus c2 b2 and c3. So the point I was making earlier about b3 can be written in terms of b1 and b2, similarly b4 can be written like that. That becomes 5b1 minus b2, right, plus c5 times b5, and if I tweak it a little bit, right, that becomes c1 minus 3 times 3 times c3, sorry, and this is b1, and again c2 b2, sorry, not c2 b2, it is 2 plus c2 2 plus c2 plus 2, and again here this is minus c4 times b2, and there in the term here minus c1 minus 3 times c3, and 5 plus 5 times c4, and then 5 times c4, right, times b1, and then you get here is plus c5 and b5. Okay, so again we can see here, because c1, c3 and c4 are scalar, of course their addition and subtraction will also generate a scalar quantity. This will also generate a scalar quantity, and this will also generate a scalar quantity. So the v here, any vector in the column space, v is any vector in column space of A, any vector in column space of A can be simply written from b1, b2 and b5 here, right? And we can actually see here that since b1, b2 and b5 cannot be written in the form of one another, it means they form a linearly independent set. So basically all the vectors column space of A can be spanned by b1, b2 and b5. Okay, and again these are actually linearly independent, because one of the simple indication of linear independence is that one vector cannot be written in the form of the combination of other vectors. Okay. Okay, now the thing here is the pivot columns. So we can say here, simply say here, the pivot columns of a matrix A form a basis for the column space of A. Okay, so it is much easier to find the basis of the column space if we can at the pivot columns of matrix A. Okay, now so what we have to be careful is that we have to use the pivot columns of A for the basis of column A. We have to use pivot columns of A for the basis of column A, for the basis of column A, which is the subspace. Remember, this is subspace. The columns of an echelon form of A, which is B, echelon form, let's say B, are often not in column space, of A, right? See, for example, if I want to give you an example on that, right? So let's say this matrix A, which is 1 minus 2 2 3, 3 minus 2 3 4, 3 2 0 minus 1, 2 minus 8 7 11, minus 9 2 1 and minus 8, right? And now look at this matrix B, which is equals to 1 0 0 0 0 1 0 0 minus 3 2 0 0 5 minus 1 0 0 0 0 1 and 0. See, you can see here that what you have just written over here, the columns of an echelon form, let's say B, are often not in column space of A, because you can see here this last row is actually 0, and there is no way I can generate the space of this dimension, right, using this matrix B, right? So we can see here the columns of B all have zeros in their last entries, right? And it actually cannot generate A. So what you have to do is always use the pivot columns of A for the basis of column A. If you use any reduced echelon form to generate the basis here, might not be useful, because see, this is here is 0, and what you can do, because both are the same thing here, this B is in reduced echelon form of A, right? So it cannot actually generate a matrix A, right? So if you choose this as basis, this is much better. If you choose this cannot actually generate the matrices in or the vectors in A, right? Both are the same thing. A is the reduced form of B. Okay, so you have to be really careful about that. This marks the end of this topic. So the topics that we have covered so far in this lecture is what we have done is revised LU factorization, afterwards we have seen an application of how LU factorization can be used in electrical networks. Similarly, we have defined the subspaces of Rn, okay, and then we have discussed the properties of the subspace, and then we have defined the subspaces corresponding to a matrix, which is column space, and null space of a matrix. Okay, and then what we have done here is we have discussed how to find the basis for the subspaces, right? And this is a very important topic, because we want to represent the subspace using minimum number of vectors. Like, for example, in the case of 2 dimensions and 3 dimensions, right? Say for example what we write here is 2 dimensions here, x and y. So right, so x and y are actually the basis for the 2-dimensional subspace, right? And said 2-dimensional space. Similarly, this is okay is actually the basis for a 3-dimensional space. So now similarly you can think of, let's say, the similar scenario here. So x, y and z, right? If you write x, y and z, so this is 1 0 0, and you got 0 0 1 0 0 1 0, and then you got here is 0 0 1 here, right? You can think of this as the basis for that subspace. Okay, right? So this marks the end of this lecture. If you have any questions, please leave a comment or comment on the discussion tab in Canvas. I look forward to your inputs, and hopefully see you later in the next lecture, which will be hopefully done by Tuesday. And the date will be, I think, that will be 31st March. Okay.